Okay, so here we've got an unidentified compound. We've been told it contains carbon and hydrogen. And what we're trying to do is work out effectively the empirical formula of the compound, right? So how am I going to approach this? Well, one of the first things I'm looking at is, okay, well, what information have I been provided in the question? So I've been provided some numbers, some percentages. These are percentages by mass, effectively, of what the compound is composed of. Okay, so, and I'm going to do a check and say, well, does it add up to 100? Like, do these percentages add up to 100? Is it approximately, roughly, or is it exactly, for example? So I'm going to just do that quick maths. I would suggest if you have a go at that as well, to see what you get from doing that. But here it's going to be 93.75 from the carbon plus 6.25, right, which is from the hydrogen. So if you calculate that, see what you get. And if you had a go, well, you should have found that you got 100, right? So it is 100 in this case. And this is just important because sometimes it isn't. So it's valuable to know if you're making an approximation in subsequent steps or not. Effectively, it's good to have an idea of what kind of assumptions you're making. Okay, so in order to solve this, to get to the empirical formula, we need to remember what the empirical formula is, right? So that being the simplest whole number ratio between the atoms of each element present in a particular compound. And in this particular case, we have these percentages by mass, but these are not directly amount of substance based calculations. It's not so straightforward to compare them because we know that carbon has a different relative atomic mass than hydrogen, right? So we would need to get this into, we need to look at the information we have through a lens that enables us to really make a proper comparison between specifically amount of substance, right? And in this case, converting this to moles and establishing a molar comparison is what is going to enable us to do that. So how are we going to do that? Well, if we recall from the equation, that links and shows the relationship between moles and mass and molar mass, we know that when we have a mass, that is effectively, and this is in grams, right, that is equal to the moles n multiplied by the molar mass, right, which molar mass is going to be in, as you know, grams per mole, right? So if we make moles a subject, what are we doing? So what we're going to do is we're going to divide both sides by the molar mass to make moles a subject. If we do that, so divide this by the mr, right? Effectively, I mean, you'd be dividing the whole thing, right? Effectively, on this side, this would cancel, and you're left with. And if I make moles a subject, what do you get? You get, well, that the moles is equal to the mass in grams divided by the molar mass, right? In grams per mole. Okay. Now we're going to use this equation, but we need the masses first. And currently we have percentages by mass, but we don't actually have a specific mass. The question doesn't say we have a particular number of grams, right? But we do need a particular number of grams to progress this question. So to solve for that issue, we're going to make an assumption. We're going to assume that the sample we have, that way we are doing these calculations with, has a total mass of 100 grams. And that takes us to a point where we can actually use these percentages by mass to establish concrete figures of mass for the purpose of molar comparison, right? So what we're going to do is, okay, therefore for carbon we've got 93.75 grams. For hydrogen we're going to have 6.25 grams, right? And well, at this stage we're going to need the molar masses, because what we want to do is convert this to moles, right? We want to create the molar comparison, so we need the molar masses. Now, you probably already know what the molar masses for carbon and hydrogen are, right? But I am going to show my working, just to show that, you know, this is, you know, to show the principles that I'm actually applying, right? So here we've got the carbon, right? And if I scroll, we've got hydrogen as well. And we can see the relative atomic masses here. So 1, and in this case 12, and it's also written here, I've got it separately here. So we can say, and I'm going to write, just have these there, I'm going to write this next to, so the molar masses are in this case, we're going to put them in grams per mole, right? And the molar mass of carbon, as we saw, based on relative atomic mass, we say that's going to be 12, right? 12.0. In the case of hydrogen, so MR of hydrogen, as we saw here, right? So that's going to be 1, right? Okay, so now using these figures, we can effectively divide these masses by their molar masses and establish a given molar ratio, right? So I'm going to divide that by 12, I'm going to divide that by 1, and then let's see what ratio we get. So I invite you at this stage, try and calculate these values and see what you get. You shouldn't really need a calculator for this, but this one, you know, maybe that would be helpful. So okay, if you've tried to work out what that is, what you may have found is that for carbon, and I'm going to give my actually this, so having calculated this, is to 4, released to 4 decimal places. There's no need to, no actual need to round it. So okay, so this is okay, 7.81. This gives 7.8125, and obviously we don't really need a calculator for this, so it's just going to give us, no wait, no, it's not going to give us 1. It's going to give us so I said we don't need a calculator, but the answer I wrote is, it's going to be 6.25, right? Not 1. Yeah. Okay. So what do we have here? Do we have whole numbers? So we're looking for the simplest whole number ratio, right? Which we don't have at this stage. We have, I mean, both of these values, if we were to round it to 1 decimal place, 2 decimal places, etc., we still would not have whole numbers, right? But we can force a whole number to appear by dividing both sides by the smallest number, and that smallest number, when we do that process, is going to become 1, right? We know that. So so in this case, what is the smallest number? In this case, the smallest is the 6.25. So you're going to divide both sides with that value that we know corresponded to the hydrogen, the 6.25, and see what we get. Okay, so if we do that, on this side, of course, we just get 1 simply, and on this side, well, I invite you to have a go. If you do calculate it, you should find that you got 1.25, right? Now at this stage, we need to engage in a process of scaling up, right? By visual inspection, it may actually be obvious to you what's going to achieve a whole number ratio in this case when we're doing our scaling up process. But nonetheless, I'm going to go through the process as we would approach this. So, and I'm going to make specific consideration to this side, right? This side obviously is already a whole number, so regardless of what we multiply it by, in terms of if we multiply it by an integer, the outcome is going to be an integer, right? This is the main sticking point currently. And we consider, okay, it could be multiplied by 2, maybe by 3, maybe by 4, but which one's going to give us a whole number, right? So if you consider 1.25, right, times 2, what does that give us? Well, that would give us 2.5, right? Now, is 2.5 a whole number? Clearly, it isn't, right? Now let's consider another multiply. So we go up this step in the scale up process, multiplying it by 3. Now, does this give us a whole number? Well, this is going to give us 3.75, right? Which, as you can see, this still is not a whole number. So we go and progress further. So multiply it by 4. 1.25 by 4, what do we get? Well, at this stage, we're going to get 5, right? Is 5 a whole number? Of course, yes, 5 is a whole number, and therefore, given we know that when we multiply whatever we're going to multiply the 1 by, if it's an integer, we're going to get an integer. So therefore, and this is the smallest, multiplier we found that effectively, quote unquote, fits the bill, right? Therefore, this is going to be actually our multiplier in this case. It's going to be an x4 times 4 multiplier. So what we're going to do here is, okay, well, on this side, we're going to multiply both sides by 4. So both this and this by 4. Therefore, we're going to get 5 on the respect to the carbon, and with respect to the hydrogen, we're going to get a 4, right? So is this our simplest whole number ratio? I say yes, this is now our simplest whole number ratio, and therefore we can say that corresponding with the carbon is going to be a 5, and corresponding with the hydrogen is going to be a 4, right? And this effectively gives us an empirical formula of C5H4, right? So in this case, this is what the empirical formula is going to be. And so that effectively solves the problem that was asked. Some other considerations about this. So this is, as we just explained, is an empirical formula. However, in generally speaking, if we were, for example, to assume this to be a molecular formula, there are actually some molecules which have a corresponding molecular formula. Even though, sometimes you may expect in many hydrocarbons that the number of hydrogens would be maybe more than the number of carbons. Actually, there are some occurring things that occur which whereby it basically has this molecular formula. Now, one example is a compound called effectively spiropentadiene, right? So spiropentadiene. Now, this actually has a nickname. This molecule has a nickname. When I draw this structure, you'll see why the nickname applies. But one of the nicknames is actually given, or what's known as, is actually bowtiediene. Let me just bowtiediene, right? And effectively, the structure looks something like this. Effectively, like this, right? Whereby these are actually all carbons, right? So you can see there's 5 carbons, 1, 2, 3, 4, 5, right? And based on the valency of carbon, you can see, like, this carbon here is going to have it's bonded to 4 other carbons, so there's not going to be a hydrogen here. And this, you can see there's the double bond, so each of these carbons already has effectively 1, 2, 3 bonds, 1, 2, 3 bonds. So there's going to be only, like, in terms of the hydrogens, right, you're going to have 1, 2, 3. You're going to only have 4 hydrogens, which corresponds, C5. So 1, 2, 3, 4, 5. H4, 1, 2, 3, 4. So as you can see, it's maybe not so easy to see it from this perspective, but if I draw it horizontally, right, so like that, you can kind of see now how it gets its nickname, right? Bowtiediene, right? because like obviously you can, you know, right? So yeah, bow tie dyeing. Okay, and there is actually another compound. So there's one other one which you could look at. However, one of the things actually which may be with regards to bow tie dyeing is actually not that stable really, because well, there's a lot of if you look at the bonds. So this doesn't give a good idea of the bonds, but and this is maybe more looking at stereochemistry, but the so if you look at the look at this, you can see effectively there's effectively some strain here. I'm not going to go into explaining this because this is obviously not the focus of this video, but this effectively shows that there's like quite a bit of strain between, it's twisted, like it's very awkward position, and generally it's quite unstable molecule anyway. And well, there's another molecule, right? It's called 1,4-pentadiene basically, right? And this is actually another molecule which has the same formula, C5H4, right? Right, so this is what that looks like, right? So one of the things you might notice looking at this is well, this carbon has already 4 bonds here, 4 bonds, and this one has, well, it's got 3 bonds, so you've got 1, 2, and then obviously you would have the hydrogen, you'd have 2 hydrogens, right? Effectively, so you can see 1, 2, 3, 4 in terms of hydrogens, and then carbons 1, 2, 3, 4, 5, right? So that again corresponds with C5H4, and that was 1, 4. 1,4-pentadiene. So you can feel free to look into both of those, but this is obviously not. This is just more of an something you can look into, less so corresponding to the empirical formula calculations directly. Okay,